you pinging me or? Oh, you see, I couldn't see that window. I just heard like pinging noises because I'm like sharing these slides. So. Okay, so okay, you want me to start, but you don't. I can't hear you on your end. Okay, all right. Well, that's good because that means I won't have to answer any questions. Yes. I don't know. So, well, unless I go back and read the window, I guess. Okay, so I'm guessing you've already seen this slide on the screen for a while. Uh, but yeah, so I'm going to be talking about several papers that we've worked on at Facebook AI Research, and so there's a lot of co-authors there on that list, and that's because there's several papers. Um, so Jesse, Andrea, Zhang, and Sina have been interns at Facebook. Uh, some of them are coming back as well this summer, and everyone else there is basically a researcher in the lab, and Thomas is there with you. So yeah, so that's basically the team. Um, and so the thing we've been interested in is trying to build end-to-end dialogue agents, and that basically requires natural language understanding and understanding of how to communicate. So while sort of internet companies like Google and Microsoft and so on have been trying to build kind of like dialogue agents like Google Now, Cortana, and Siri, all those kind of things are just kind of engineering systems with a set of separate black boxes with like joining logic that can do some tasks for a user, but they don't really end up as like a true, dialogue agent that has some kind of smarter AI. For example, we think, a true dialogue agent should be able to combine all of its knowledge to fulfill complex tasks. It should be able to handle long, open-ended conversations, which, may involve sort of tracking lots of latent variables. And it should be able to learn new tasks, during conversation, remembering new things, and so on. And, those are sort of examples of things that I believe those systems like Google Now, Cortana, and so on cannot do. So our bet is to use, sort of end-to-end machine learning and trying to learn an end-to-end system to do these things. And we believe that's the way forward in the long run, but obviously this, we're not here yet, and this is going to take a while, so it's kind of a long-term bet. But, that's research. So, yeah, so what we're doing here in this talk is basically we're saying that our long-term goal is to, get one of these end-to-end learners and be able to train it, possibly from scratch, to understand and use language, for communication. And our main interest is to uncover the learning algorithms able to do that. And in order to uncover the learning algorithms that could do that, we need training data. Okay, and so inspired by a roadmap towards machine intelligence by Thomas, Armand, and Marco Baroni, we advocate making a set of training tasks and evaluation, which also come with evaluation data, so that we can train and evaluate on these disparate tasks to try and understand, what is the learning algorithm that we need. Try and uncover what the learning algorithms that we have already are able to do, and try and inspire by looking at their failures how to design the next set of algorithms that are, able to do more than the ones we have right now. And so the data sets that we've looked at are listed here, and so some of these are things that we've built at Facebook, and some of them are existing data sets. So the first things I'm going to talk about are question answering in a toy like simulated world, which we call baby tasks. And those are toy data, and we think toy data is useful for trying to understand what's wrong with current models we have, and for designing, when we design new models, to try it out on that toy data and sort of see how it works. But we don't think toy data alone is enough. We also need real data. So the other three things in the list there: story understanding, open question answering, and goal-orientated dialogue and chit-chat. Those are kind of more real data sets using real natural language. In particular, story understanding, we've looked at a data set we've built called the Children's Book Test, which takes children's books from Project Gutenberg and tries to see if the learner can understand the story by filling in missing words. And we also look at the news article data set, which is kind of a similar related thing by Google DeepMine. For question answering, we look at the well-known web questions data set and a data set we've built at Facebook called Simple Questions, which has a larger training set. And then finally, we've built another data set called the Movie Dialog data set, which takes dialogues from Reddit, plus some other things that we built to try and see if a learner can conduct dialogue about movies. So there's a lot of different data sets here, and they're all sort of designed to try and test different skills of an end-to-end machine learner. So we can see basically which skills it can and can't do, and then try and understand what's the next step. So the first thing I'm going to talk about are the toy data sets. So these are the baby tasks. Did I hear a microphone? Maybe you've got it working. So these tasks are generated by a simulation of a very simple world with like characters and objects. Looks like a text adventure game, and we have 20 different tasks in that simulation that test different skills. And we look at this kind of like software unit tests, so that basically you can see whether you sort of pass or fail each of these 20 tests. And we sort of set them up so that we believe that humans should be able to get 100% on all these tasks, so that and we basically say that if a learner gets more than 95% accuracy, then we call that a pass, basically, and everything else is a fail. I mean, there's other ways you could evaluate it, but this gives you a nice, easy sort of way of doing a system check. So the simulation looks like this. You have these kind of text adventure game kind of instructions, like go, get, put, give, drop, and so on. And then you have characters in the adventure, like, for example, Jason, go kitchen, Jason, get milk. These are instructions in the simulation. And these ones, using a simple grammar in the code that generates the toy data, you can convert those commands basically into something that looks more like natural language. I mean, it's just a subset of English, basically, a very simple subset of English. And so, given that you've got this description now of a little story of what's happening in the world, you can then ask questions. Like here, you could ask, where is the milk now, or where is Jason? And you know the answers because you have the underlying simulation. So that's the way we build these 20 tasks. So the very first task is kind of very simple. It's just going to be like you have one of those kind of stories, and then we're going to ask, where is one of the characters? So in this case, where is John? And the answer is playground, because you can see in the story above, in the sentences above, that you have John is in the playground as one of the statements. So we call the statements that you need, required to answer the question, supporting facts. And I mean, this is just a phrase that we use here, that it's kind of which we can use to kind of see a little bit how complicated the question we are asking is, because we can make a slightly harder question that requires 2 supporting facts instead of 1 supporting fact here. So if you ask the question, where is the football? Given this little story, John is in the playground, Bob is in the office, John picked up the football, and then Bob went to the kitchen. You can see that you need both the sentence, John picked up the football, to know that John has it as one of the supporting facts, and that John is in the playground as the other supporting fact, to be able to answer the question with the answer playground. So, and things could get even harder, like you could require 3 supporting facts, like for a question, where was the apple before the kitchen, and so on. So we could look at, just going back to the slide of task 1, we could look at the kind of supervision we have for a learner as just, for an end-to-end learner, you'd think you would just have the story, the question, and then the answer, in this case playground, the text in red. So that would be kind of, the input is all the story plus the question, the output is playground, and that would be kind of, you need to learn your end-to-end system to predict that right output. But you could also look at what we call a more strongly supervised case, where you actually supplied which are the supporting facts at training time, but not at test time as well. And this would be useful for methods that are not end-to-end. And we're going to compare against some of those, which is why I mention it. And some of the first models we made used that kind of strong supervision, which we don't think is a good idea because it's very restrictive. That a lot of data sets might not actually have that information, that strongly supervised information. But still, if you have it, it's interesting to see how much better you can be if you have this extra information. So that's the first 3 tasks. I'm not going to show all 20 tasks because it's going to take too long. But let me just quickly mention a couple. So they're designed to test different things. So the first 3 were testing like different numbers of supporting facts. The 4th one, the statements get a bit more complicated. So they have subjects and objects, and tries to test whether you can identify the difference between them. We have tests of whether you can answer yes/no questions, which it turns out you need kind of more nonlinearity in a model to do that. We test whether a model can count things, like how many objects Daniel is holding, whether it can produce lists, like what is Daniel holding, in that case the milk and the football in the little story at the bottom there. Whether a learner can handle co-reference, so like Daniel was in the kitchen, then he went to the studio, where is Daniel? And time manipulation, so like can we understand the words afternoon, yesterday, this evening, which are going to change the time order. It's no longer just a sort of a linear sequence of the story, because you could refer back to something in a different sequence, like a Tarantino movie does, or something like this. So yeah, we have a basic deduction, like here in this simple example, sheep are afraid of wolves, Gertrude is a sheep, what is Gertrude afraid of? In the most difficult case, deduction should be tricky for learning models, because it effectively is going to involve some kind of search, which not every model has, end-to-end learning model has built inside it. We have, I'll just skip these 2 and just go to this task 19 here. It's another one where you might need search. It's a pathfinding task. So you have in the statements kind of which locations are connected to which locations, and then you have to find. The question basically asks you to find your way through the maze, if you like. So how do you go from den to kitchen? So yeah, so a lot of different tasks. And we can now test a whole bunch of different machine learning models on them and see what we've got. So out of the models that exist today, what do they work on, what do they not work on? And when we find what they don't work on, maybe this can inspire us to come up with new models. And if the models do work, then that should inspire us the other way around to try and make new tasks that don't work. So we can have this kind of hopefully virtuous circle for conducting research. So the models we try are a kind of classic NLP cascade using SVM structs with a whole bunch of features to do the subtasks of finding the supporting facts. So this isn't end-to-end, but it's good to compare against. We try an SVM type classifier with n-gram features. We try LSTM recurrent neural nets. And at Facebook, we've also sort of been developing a new class of models called memory networks that we're also going to apply to this data. So I'm going to spend a bit of time now just talking about memory networks, and then I'll show the results of these models. So yeah, memory networks are kind of a class of models that combine a potentially large memory with a learning component, in this case a neural network, that can read and write to the memory. So a lot of machine learning models, kind of, if you think, say for example, of a standard feed-forward neural network, like for, say, object detection, it kind of has limited memory in a way. Like its only memory is basically in the weights of the neurons, which have to be sort of trained by gradient descent. But it doesn't really have a way of having a fast writing to memory as it's sort of, for example, reading a story. So this was kind of our motivation for developing these models. It came from this sort of dialogue, language understanding motivation, where a long-term memory is kind of required to read stories and also, say Wikipedia pages, and then sort of, remember relevant facts if you want to answer questions about them later, or remember a story if you want to answer questions about a story later. So this is kind of the goal. We're first going to test this on the baby task I just showed you, but any interesting model has to be good on real data as well, and so we'll get to that afterwards. So here I'm going to talk about the end-to-end memory networks of Sina, Arthur, myself, and Rob Fergus. And this just little picture here is basically on the right showing the original story, and at the bottom left is one, the question you're about to try and answer. And sort of the first thing that happens is the story gets read into the memory of the memory network. That's this thing on the left, and it gets converted into basically some kind of feature representation. That's these M1, M2, M3, M4. They're basically going to be vectors. So each sort of memory location is going to have a vector, which sort of is the feature representation of that part of the story. And then when the network tries to answer a question, it's basically going to take the question, it's going to sort of look through its memory, compare the question to each part of the memory, and see if there's anything relevant in the memory. So basically it's going to look for what we call the supporting facts, because those are the ones that are needed to answer the question. And as you saw in the toy data, sometimes there's more than one supporting fact, right? And it can happen that you can't actually find those at the same time. You may need to find one supporting fact first, and then you can only find the second one conditional on the first. So for this reason, we kind of go linearly through the memory multiple times. So in the first, what we call the first hop, you try and find some supporting facts, and then conditional on the supporting facts, we go through the memory again, looking for more supporting facts. So that's kind of basically the idea. So the overview is, yeah, it's a neural network model with an external memory. It reads from this memory. It's going to end up doing that with a kind of soft attention mechanism, trying to pick out those supporting facts. It's going to perform multiple lookups or hops, as we call them, on that memory, and the whole thing is going to be end-to-end trained with backpropagation. So this so-called end-to-end memory network is kind of our second iteration of memory networks. So the first one, the first iteration, it was just called memory networks, not end-to-end memory networks, because it didn't have the end-to-end part. It actually had, so it was kind of basically the year before, it had a hard attention mechanism instead of soft attention mechanism, and partly due to that, it wasn't easy to train that thing end-to-end with backpropagation, and in our first experiments, we were required to have an explicit supervision of the attention, i.e. of which are the supporting facts during the training. And so that was what I was referring to as the strongly supervised case on the earlier slides. So this is only feasible, well, it's only feasible for tasks where you have that strongly supervised training data, which severely limits the application of that first variant of the model. But still, we can, on this data set, we can compare them. Whereas the MEM end-to-end, it only needs supervision on the final output. So here I'm going to just have some pictures which go into a little bit more detail of the MEM end-to-end architecture. So you have the input at the bottom there. So that's basically the memories from the story. This is this M1 to MN, and the question, which is going to be turned into basically the state of the controller module, U1 here. It's going to be kind of initialize the state of the controller. So you have these. So there's the memory vectors, and there's the internal state. And so what's going to happen is on what we call the first hop, the state U1 is going to be used to address the memory, the M1 to MN, and then the memory module on the left is going to return a new state, U2, which is basically going to be the supporting facts that it thinks it found. And then that new state, U2, is going to be used again to address the memory and produce a new state, U3. And this is done for n hops, which is a hyperparameter, until finally we have a final linear layer which predicts the output. And that's the stage where you get the supervision, and then you have to basically, the backpropagation has to go all the way back through this to train all the weights. So let's zoom in a bit here on the memory module. So that's the thing on the left-hand side. So we have these memory vectors, which are the feature representation of the story. I'm going to talk about that in a second, how you get those memory vectors. They're basically going to involve word embeddings. So if you know things like word2vec, it's going to be that kind of thing. And then U is basically the state of the controller, which is initialized at the beginning to be the sentence embedding of the question. So what happens in this addressing stage is that basically U is dot producted with M1 to MN, giving N real valued scores, and those are converted using a softmax into probabilities, and they basically give you what we would like that to do is to give you basically the probability of each one of the memories being a supporting fact. Okay, and then finally the original M1 to MN are multiplied by these probabilities P1 to Pn to give a weighted sum, which, imagine if only one of the Pi is switched on is a 1 and everything else is a 0. That weighted sum would just pick out one of the memories, which would be one supporting fact. If there are multiple supporting facts, you would expect multiple of these Pi to be non-zero. Of course, it's a softmax, so it's going to be a continuous thing. It's not going to be, completely 0, 1 like that. And that's basically the memory module, which is used in a single hop. So, now just going back to how did we get these MI to MN? So these are the representations of the memory vectors. So the simplest thing to do is a bag of words, or a bag of word embeddings, more explicitly, representation. So if you had something like Sam drops the apple as one of the sentences in the story, you can have a word embedding for Sam, a word embedding for drops, and a word embedding for apple, and just simply add them together. And during backpropagation, you're going to train these word embedding vectors. And that gives you your memory vector, which we were showing on the previous slides. So one thing that's very important is you actually need the temporal structure. So if you didn't include some extra feature, which I'm about to tell you, which we call a time feature. You wouldn't actually know the order of the story because these memory vectors M1 to Mn are basically unordered. So what we do is we add this extra feature down here. You see V3, which says that Sam drops the apple is actually the third sentence in the story, and we train that V3 as if it's another word embedding vector. And similarly, the second sentence, Sam went to the kitchen, would have a plus V2 there. So that's something we do, which is important. Yeah, so that's basically it. This is just showing the same thing with an explicit example. Sam moved to the garden, Sam went to the kitchen, Sam drops the apple there. So those get turned into these M1 to M3 vectors. Where is Sam? We also use a bag of word embeddings to construct a U1 state vector, and then we do that dot product and softmax. So that would give you some scores like that, 0.1, 0.7, 0.2. You take the weighted sum of the M1, M2, M3 using those values, and that gives you add that on that output, 0.1 M1 plus 0.7 M2 plus 0.2 M3, you add that to the initial state U1, and that gives you your new state U2. And then you can repeat that in a second hop, or you could just, if you only had a one-hop model as shown here, you would then just have a final linear layer which has a prediction, a probability of every word in the dictionary to give you the probability of outputting the word kitchen. I mean, then you simply take, say, the max over that and predict that word, and that's where you get your supervision and backprop through all these weights. So basically, that's the model. I mean, this is not the only model around right now which is trying to sort of take neural networks and try and add some memory to it, and it's not the first one either. So I'm listing a few here. So there's sort of people adding attention to RNNs. So one such paper is RNN Search by Badenow et al., and they were using that for machine translation. There's also other work in our group at Facebook by Armand Gillan and Thomas Mikaloff, where the memory is not kind of like an array like in the memory networks, but it's a stack kind of memory, and they've sort of bolted that onto the recurrent net. Some nice results. There's neural Turing machines from Google DeepMind. There's also a whole bunch of new papers coming out. You can see it, like say this iClear, where the papers are online at the RAM workshop at NIPS last year. There was also a bunch of stuff, and I'm just referencing a few things here from the 90s as well at the bottom here. Yeah, so lots of stuff. Yeah, but now on to experiments. So this is the list of the 20 baby tasks that we built, and then we're comparing a bunch of different models. So we have weakly supervised models in the first 3 columns here, and the strongly supervised models, the original memory networks, and not the end-to-end memory networks. They're here, the MEM end-to-end, and the structured SVM. So those are the strongly supervised ones. So you can see those ones kind of do a bit better. They've basically got more of these green pass fields. So that's where you have more than 95% accuracy. But that's kind of not really a realistic setting. So you can see MEM end-to-end is not doing too badly, given it has like less supervision. It has a number of passes. And like the ones it's failing on, like pathfinding, these strongly supervised models are failing on that too. Basically, none of those models really have a kind of search mechanism inside to be able to do well on that. Whereas on the 3 supporting facts, so task 3, the strongly supervised case is working there, but the mem end-to-end is not. So that's more a case of the model could be able to do it if it found the right configuration of weights, but the lack of supervision is inhibiting it there. Whereas I would say on task 19, the failure is not because during training it couldn't find the right configuration of weights, but more because the actual model is unable to solve that task at all. We need to look at different models. Yeah, so and LSTMs, standard LSTMs are kind of quite a bit inferior here. They do not have an attention mechanism, and they're not really able to remember things from the story very well, and that's basically their failing. So those are kind of some results. You can sort of go in and look at the attention on some of these stories, and you can see. So this is of the end-to-end memory network, and you can see it's like picking out the right supporting facts. So here I'm showing the P1 to Pn, right? This is the probabilities of the softmax, and say on this story 2 here, you can see that. So the question is, where is the milk? It's finding John took the milk there should be like a supporting fact on the first couple of hops, and then on the third hop it kind of links that to the other supporting fact that's necessary, that John moved to the hallway, so that it can finally answer the question with the answer hallway, which is right. So yeah, and you can look at the error rate as you basically increase the number of hops from 1, 2, 3, and you can see that it's basically improving. So this kind of hop idea is important here. But we're still failing on some tasks, and as I said, hopefully we can make a feedback loop here in the future of developing models that can solve the tasks we've already made, and developing new tasks that break models and try and lead us in a future fruitful research direction. But while toy AI tasks are important for developing innovative methods, they don't give us all the answers. And I think we really also need to see if these models work on real data to keep us honest. So that was kind of like all these other data sets that we've looked at. So the open question answering, the story understanding, and the goal-orientated dialogue. So going to talk about these now. I actually have no idea how long I've been talking because I don't have a... Can I see the time? 11:17. Okay. I don't even know when I started because we were so late. But how much longer have I got left? Can you tell me? Oh, maybe you don't have a microphone to even tell me. Can you just chat it? Or no? Okay. Never mind. All right, I'll just carry on. So yeah, so one kind of real data set we look at is large-scale question answering. So here, the memory isn't going to be one of these toy little stories from like the baby tasks. It's going to be like a huge number of facts from Freebase. So we look at like 22 million facts over 5 million entities, and then we can answer questions like who created Gollum from The Hobbit. We have this huge memory where you can see this is just a few examples from that memory, and it needs to kind of look over that, find the right supporting facts, and then answer with the right answer. In this case, J.R.R. Tolkien. So we might also need some kind of hashing or string matching for fast lookup in that case in the read module, because otherwise we're linearly scoring like 22 million memory locations, right, which is going to be a bit slow. So we've done things like that. Yeah, just to summarize, basically on web questions, which is a popular QA task like that, we have a performance, this is F1 scores of 42, which is kind of basically was in line with a lot of other models that people have been building, which kind of aren't as end-to-end, I would say. They have like a lot more engineered features in them. But more recently, yeah, it was at ACL last year, there's even better results. So someone's got 52.5. That's the highest one I know, which again has a whole bunch of hand-engineered features. So we don't have the best results, but this model is kind of in the ballpark. And the nice thing is we know that kind of model is also working on the baby tasks, which basically these other models that people have developed specifically for web questions, question answering, they just don't work in other cases, like on these stories that we've shown before. So what we're really looking for is a model, an end-to-end learning model that can work across all these different problems, not kind of hand engineering algorithms for every different task. That would be a nice thing, we think. So yeah, so that's where we are with large-scale QA. So we've also been building this children book dataset, which I mentioned at the beginning. So here we took 118 children's books from Project Gutenberg, and we built a dataset by taking passages from the books where we have basically a context and then a question. The context consists of the last 20, or no, last 10 sentences here in this example, but I think actually it's 20 in the actual dataset. But and then the followed by one sentence which is going to comprise of the question. And the question is basically we take just one word kind of in that sentence and blank it out. And then the question is, can you fill the blank? So here it's like his 3 youngest boys in his lap and blank hovering over him like a large-sized cherub. So we set it up as a multiple choice problem. So we have 10 possible choices, and in this case here, Archie is the right answer for the blank. So we make a whole bunch of training data using those children's books that looks like that. And this is sort of reminiscent basically of the DeepMine news dataset, which I could just show, looks like this, which we also do experiments on. So in their work, they, rather than having children's books, they have news articles. So they kind of look like this, where there's a context and a query, and again they have this blank. So producer blank will not press charges. So they've done something where they actually anonymized all the entities. So this anonymized version here is on the right-hand side, and the blank you have to fill then is like anonymous entity 193 rather than the real word. Whereas in the children's book data, we have not done that. But other than that, they're kind of related data sets. So these are these two kind of data sets. So we can use our end-to-end memory networks on these as well and see, do they work on this kind of real data? So again, you basically have to take the story and sort of dump it into the memory on the left-hand side, produce these memory vectors, and just do exactly the same procedure to try and answer a question. So there's a couple of questions that we asked here which are a bit different to before. One of them is, how do we actually build the memory? So we looked at, rather than just sort of dumping each sentence as one memory location, we thought maybe we could try different ways of building the memory. So either at the sentence level or at a window level. So we have a sort of sliding window over the text, and sort of each memory location is now one of those windows, or even at the word level. So now each memory is just a single word. So you can sort of look at these 3 levels of granularity, and we sort of compared results with those 3 sort of ways of doing things. And we also looked at one other trick where we have a heuristic for self-supervision of the supporting facts. So in this data set, we don't have strongly supervised case, right? So we only have basically the answer. But what we can do as a heuristic is we can look over our memories if they have any word overlap with the answer. And if they do, then they may be good, candidates for supporting facts. So we also looked at this with and without this heuristic of sort of also trying to basically increase the probability of memory locations that seem to have overlap with the answer. So that's sort of another trick we did. So that kind of explains some of these results. So we tried a whole bunch of different models on this children's book test. So at the bottom here we have the different kinds of mem end-to-end. So lexical memory, that means that the word level memory, the window level memory is after that, and then the sentence level memory, and then this final one here, window memory plus this self-supervision trick, is that heuristic I was just telling you about. So the data set is actually divided into 4 kinds of question, which are basically different type of blanked out word. So if the blanked out word is a named entity, if it's a common noun, if it's a verb, or if it's a preposition. So it was interesting to break it up in this way, because you could see actually different behavior from different models for the different classes of word. So for example, LSTMs are very good actually at verbs and prepositions. In fact, they're on par with or better than humans. So we actually, because we set this up as a multiple choice problem, we actually got human annotators to read our stories, our little 20 sentence context plus query stories, and try and answer the multiple choice questions. So this is basically their accuracy at the multiple choice. Here, say humans, given the context plus the query, they get the right answer for named entities 80% of the time. That's what that means. If they're only given the query, so that's the final sentence, and not the context of the story, humans do significantly worse. They go down to 50%. So this is interesting, because if you look at LSTMs, where you have either the query or the context plus query, they don't actually change much in their performance. And what that's showing is that basically they don't have a very good way of storing the context, right? They don't have a very good way of storing memory. Yeah, so basically the upshot of the results is that for the mem ends, the window memories for named entities are actually working a bit better than either the word level or the sentence level. So there's kind of a sweet spot in the size of the memories. So that's sort of something one can tune or try and understand, and that this self-supervision heuristic gives you a boost as well. So overall, once we have the right size window memory and this heuristic, we have like pretty good results, well, better than other methods we tried for the memory networks for the named entity and common nouns. So that's where we are there, and then we apply basically the same method to the DeepMine dataset, and we got some pretty decent results there. So basically the first 6 rows are like the results from the DeepMine paper, and then we have these variants of MEMNN that we tried. So with and without the self-supervision heuristic, and when we add like an ensemble of training multiple of these MEMNNs. Yeah, so in the best case, we get around 68, 69, which is somewhat better than the best results in the DeepMine paper, which are like 63, 64. So that's where we are there. Yeah, and then the final set of data sets that we built are these movie dialogue data sets. So everything up to now has not really been dialogue, right? It's been more kind of question answering. But what we'd really like to do is have an end-to-end learner that's able to, conduct a conversation. So there will be an exchange of, multiple things that are said. So this is the goal of this data set, the movie dialogue data set. It's closed but large domain about movies with 75,000 entities, around 3.5 million training examples. And there's kind of 4 different tasks. The first task is more like a straight question answering task, which asks facts about movies. The next one asks for opinions, the second task, which are recommendations about movies. The third task is a sort of combines the two and asks for like facts and opinions in like several exchanges of conversation. And then the final one is kind of general chit chat, where we took like Reddit chats from the subreddit about movies. And then the goal is, can you combine all of these in one end-to-end model? So yeah, I'm just going to really quickly show that data. So this is the sort of task one. These are the kind of factual questions. Can you name a film directed by Stuart Ortiz? And what is the genre of the film? Dial M for Murder, and so on. So task two is a recommendation task. So we have, some movies I like are Heat, Kids, Fight Club, Shaun of the Dead. Can you suggest something else I might like? And then we want our model to output, in that case, Ocean's 11. So this is taken actually from Movie Lens data. So that's kind of like real recommendation data. And then you can make combinations of that, so it actually looks more like an exchange. So you've got the human, if you like, who's saying, I loved Billy Madison, some other movies, and then I'm looking for a music movie, and then the reply that we're supposed to learn here is School of Rock. And then in the next line of the conversation, the human's asking, well, what else is that about? And then kind of the learner has to answer what are the things that School of Rock is about. And then there's another bit of conversation where the human says, well, I like rock and roll movies more. Do you know anything else? And then the recommendation has to change. So here we actually have more like a real dialogue. And, you have to combine several things, basically. You have to combine kind of short-term memories, which are basically the lines of dialogue that happened so far, and long-term memories about facts that you know about movies. So here's an example, basically, where that's happening. And finally, the last task 4, is the stuff directly from Reddit. So this really looks a lot more like just general chat. So here's an example. And there could be multiple lines of dialogue. Here I just showed 2 lines. Yeah, and that's basically, we built that data set and we tried a bunch of models, and we're hoping that's going to be a benchmark that other people can use. So I just want to basically end there and say, so we got 2 different types of things. We have these artificial tasks, the toy tasks, that we're hoping can sort of check the skills of models and motivate designing new models. And then we have the real tasks that are kind of really doing a sanity check if these models that you're building are actually working on real natural language. Yeah, so our group is producing a lot of stuff. So here's some of the things we produced. So these are kind of all the relevant papers to this talk. We have released all this data, the baby task, simple questions, children's book test, and the movie dialogue data set, and they're all online. And we have released code for memory networks and the baby task simulation as well. And yeah, and that's it. No idea if I took too long, sorry. Okay, so am I going to be able to hear you? Or? I cannot hear you. I see you tapping the mic.
Раз, два, три.
Hello?
Так. Так, все он слышит, но его нет. Так что давайте похлопаем для начала.
Oh, I had some applause. Thanks.
Вот этот микрофон. Так, ну у кого есть вопрос? Вот говори, будет слышно.
Hope you can hear me. So,
Hi.
my first question is, how do you deal, I mean, that's a technical question, how do you deal with very large contexts? Do you throw all 1,000 sentences into the memory of a memory network, or maybe it could be a good idea to filter them with some, I don't know, search engine before throwing it to memory network?
Yeah, so ooh, got some feedback there. So I just very briefly mentioned this here in this slide, that basically the one thing we've tried is like what a search engine does. We do a kind of first pre-filtering using hashing. So we basically take, so in this case, the large-scale QA, we have 22 million memories, right? So there's, it's not so easy to linearly go through that. So what we did is simply removed all memories that don't share enough words with the question, right? And so basically we do a hash lookup. We just go across the words in the question, and then we know, all that. It's like an inverted index basically to find the right memories, and those are the only ones that we then use in the mem end-to-end, let's say, to compute the softmax over. So we've done that, but and that's working pretty well, but obviously there's a bunch of other ways you could do that, and you can sort of look at the approximate k-nearest neighbor literature and so on, or lots of other work that tries to do those kind of speed ups.
Okay, so I'm sorry. So when you have lots of answers to choose from, like several thousands of answers.
Answers.
Softmax. I mean, do you use hierarchical softmax or some other tree?
Yeah, you could. No, we haven't been doing that. We've just gone. We've just done all of them. So we've never had more than like 5 million, and that we could. I don't know. Yeah, we just computed it, I think. I don't know.
And my final question, do you know any neural system that solves this worst task of baby task, this pathfinding one?
Yeah, so there's the
or bad for the other task, but good for this one.
Yeah, so there's the what do they call it? Neural reasoner. Like it's just a paper on archive as far as I know, or maybe they have an updated version where they basically have something I think looks quite a bit like the memory network, but they have extra nonlinearities. Instead of having a dot product between the question and each memory, they kind of have a nonlinear little module there that combines things. And they showed if they have enough training data, so if you have 10,000 training examples, not 1,000 training examples, on the pathfinding, you can actually do well. But I'm not too excited about this result because that's kind of too much training data, basically. So on the 1,000 training examples, they're still failing badly. So, I mean, one thing that we did in the original baby task paper, which basically Thomas was kind of the one who proposed that, is that we also looked at how many training examples do you need to be able to pass the task, right, to get, say, more than 95%. And so sort of that's a metric that you can look at, is that number of training examples metric. And so you could look at the, say, the pathfinding task, how low can you get that down? And at the moment I don't think there's any models that I know of that end-to-end that are getting some reasonable number there. I mean, I still think that sort of baking some sort of way of actually doing the search into the model would make sense, but I don't know if anyone's tried it.
Thank you very much.
Other questions? So we have no more questions. So let's thank Jason's one.
Okay. Thank you. Guess I'll hang up. Bye.